What is the most used man-made material on Earth? You guessed right, it's concrete. Look around, it's everywhere. Sidewalks, driveways, foundations, floor you stand on, and even entire buildings are made out of concrete. So why don't we discuss it more? In each episode of Concrete Logic, we'll explore one concrete-related topic with the help from industry professionals that are shaping the future of the trade. We'll talk with suppliers, contractors, architects, engineers, specialists, and even some proponents of competing materials about their views of concrete and their vision of its future. Welcome to another episode of the Concrete Logic Podcast. Today with me, I got Patrick Morrissey and Alvin Ericson, a couple concrete consultants that are going to teach us some stuff today. Pat, can you start us off, give an introduction?
Sure. My background is I was trained as a civil engineer at Manhattan College in the middle of the last century, and basically never got to the level of becoming a PE. I became a materials consultant almost immediately and have been involved in the concrete industry for the past 46 years. My business card even says Think Concrete on it. What I wanted to do today was first just to introduce some of the products that we've introduced to the concrete industry, some of which became very obvious, other ones took a lot longer to introduce, but end up with a complete review of the current state of the art with regards to corrosion-free concrete. My background is I started with Windsor Probe, which was the first piece of equipment to accurately test concrete in place other than cores. We did that for many years. It became an ASTM method. And after we left that company, we opened up ConSpec. Our first venture, which sort of full circles around to our second speaker today, is I was the first rep for Forta Corporation with the Forta fiber, which was the first polypropylene fiber, and I was their first rep. So that goes back into the 80s. We introduced Mighty 150 super plasticizers before anybody else in the United States, which came from Japan. We got involved in things such as Geislich, which was the Artex competition. When back in the 90s, when we tried to convince them to top the slabs instead of finishing them, they said we were absolutely crazy. But now, in our current state of the work, everything is done with basically a cast slab, and then it's topped with a self-leveling material. We got involved with a product called Pyramid, which is interesting because that was an activated system, an activated cement, which is starting to come around full circle. It's being reintroduced to replace Portland cement in our industry. Activated cement, difference being the time between initial and final set was 5 minutes. That should open a couple eyes. We did work at the George Washington Bridge. We did work up at Logan Airport. Anywhere there was critical nature. Some projects actually had $1,500 a minute liquidated damages if you couldn't open up the roadway. But we did an awful lot of that type of work throughout the 90s, and then as we turned the corner, we did a lot of work with SCC, self-consolidating concrete, but in a bag, as opposed to the stuff that's out there today. Many of the SCCs are basically repair products that are modified. We actually introduced an SCC concrete that was in a bag that could be used for post-tensioning repair and reached 2,000 PSI in just a little over an hour. So it was ideal for post-tensioning repairs. Most of my business nowadays involves basically concrete and concrete repair. The thing that I'll talk about a little bit is I handle a product which is called Rurgold cement-based carbon fiber, which is an alternate to the resin-based systems that are out there. We're currently doing falling water. We're doing a lot of concrete repairs. We've been doing garage repair and stabilization and strengthening since 2008. And the big difference is ours is not a resin-based system. It's a cement-based system, which is totally compatible with our operation. So that's a little bit of my background in the concrete end of the business. The thing I really want to talk about today is corrosion-free concrete. And for that, the gentleman that I work and report to is sitting on the right-hand side of my screen. That'll be Alvin Ericson. I'm going to pass it on to him to let him give you a current state of the art of how to produce corrosion-free concrete.
Thank you, Pat. Appreciate it. Again, Al Ericson. I am an independent technical marketing consultant. Been doing this for decades in the concrete and precast concrete industry. My background is in education in architectural engineering and business. And my very first job out of college was with a precast concrete manufacturer up in Massachusetts. Worked for a couple of them. Then I worked for the Pre-Stressed Concrete Institute as their regional marketing director. And a lot of people in the industry today know me as the representative for NMB splice sleeve systems, which is a type of mechanical coupler for rebar, grout-filled mechanical coupler, really targeted at the precast industry to allow them to connect precast elements together and make them behave as if they were monolithic cast in place. So I stopped working with NMB splice sleeve for a few years back in 2008 and took a few years off and regrouped. And of course, we had the Great Recession and then got back into new technology again, which is what I really talk about. What I do is introduce new technology to the industry. The new technology is fiber reinforced polymer composites. And while some of these composite materials have been around for years, such as rebar, glass rebar, the people talk about it, GFRP rebar, things like that, they've been around for now maybe 30 years or so. They're still not widely used or adopted, and but that's going to change. Also, the companies that I'm involved with are now getting into making different forms of these composites in terms of not just a plain rebar, but an all-thread rebar that can be threaded and with connected with threads and nuts and couplers. And also they've miniaturized this material down to a what I call wire size, the diameter of a paperclip wire. And now we chop that into different lengths and blend it into the concrete as an alternative to, for instance, the fibers that Pat was involved with years ago. Fibers in concrete are generally classified in two ways: either you're synthetic or you're steel. And we classify this new FRP composite as a synthetic fiber, but it actually has the strength and properties and performance of using steel fiber. The beauty of it is with all of these composites, the specific gravity of the material, because they're made with what is essentially a rock-like fiber, whether it be glass or basalt or whatever, they blend very well in concrete. Concrete has we call a specific gravity of 2.4, and these FRP composites are in the 2 point something range. And so they don't float, they don't sink. Some of the contractors that are out there will take a look at fiber reinforced concrete and they'll say, oh, that's fuzzy concrete. Well, with some of the plastics, yes, they tend to float. So anyway, that's where we're starting right now. And I can take it from there. Seth, what would you like to know more about this?
Well, there's so much to unpack there, Al. Let's start off with the fiber reinforced polymer. So you're saying it is a macro fiber, or it's not?
It is. It's classified as a macro fiber. Yeah, and it's the other thing. If we get into the fibers here, and by the way, one of the things about the fibers in the rebar is they actually work well together. The fibers are classified as either micro or macro, and there's an arbitrary dividing line at 0.3 millimeter diameter. So basically stuff that's really fine, hair-like, is a microfiber, and stuff that is more like small wires, as I said, like a paperclip wire or something like that, or wires that you'd see in wiring, those are macros. And and again, it depends on the nature of what the material is trying to be produced to do. The micros tend to be just for what we call crack control. They just take care of early age shrinkage cracking in the concrete, and they don't have much. they don't impart much strength in terms of flexural tensile strength after that. The macros, whether it be a synthetic or a steel or these FRP composites now, they impart structural strength post-crack. In other words, when you start to load and flex a piece of concrete, it will, and load it up, it will, at some point, it will crack. And without anything in it, steel, fiber, whatever, it loses it right there. You've broken it. But if there's rebar in place, that rebar starts to take over. If there's fibers in place, the fibers start to bridge those cracks. And so depending on how much we put in and how much loading we're expecting, we can get various types of performance. And you can either, get very technical here. We talk about strain softening and strain hardening. And that means that we can put a little bit of fiber in and it'll help us a little bit. And you get what we call a strain softening, so it's not quite as strong as after it hit that first crack. And then we have concretes, most notably today, the ultra high performance concretes that use a lot of fiber, and in terms of dosage and whatnot, and they get what we call strain hardening, which means after that first crack, the fibers really start to take over, and there's a lot of them in there in the matrix. And what happens is they get stronger and stronger, and we actually get a stronger concrete, like we had rebar in there. So this is where the fibers can sometimes literally take over and eliminate or reduce the need for rebar. And that's one of the things that we've really discovered. I can give you, for instance, an example in bridge deck design. We just did a research project about this a couple of years ago at Utah State. And a typical concrete bridge deck in a roadway here, very typical. It's funny how these things are almost the same throughout the United States as the engineers do their designs. It will be a pattern of reinforcing in an 8-inch deck that'll be spanning about 10 feet between the girders. And in that 8-inch deck, they'll have 2 layers of reinforcing, and they'll basically be number 5 bars at 6 inches on center and 2 grids, no lower grid and upper grid. And of course, nowadays they tend to use an epoxy-coated rebar. It's very common. It's been used for years, but it has its issues. It has a certain amount of protection, but it doesn't last forever. They now talk about time to corrosion. So we started to look at what they could do, and that was the first, by the way, the first main use for the glass rebar was in bridge decks. That's where they've been focused on for years. And there's probably over 200, well over 200, maybe almost approaching 300 bridge decks now in service between the U.S. and Canada that are performing outstanding. I mean, they just tested some decks that were 25 years old. There's absolutely no deterioration to these decks, and doesn't appear to be. We're talking about 100-year life cycle now on these projects. So really, sorry to interrupt. Long life. So what we've determined, though, is that we would normally have had to take and use the same bars on a 6-inch grid with the GFRP bars, the FRP bars. But there's another aspect what I can get into, which is technical, but we have to go up 1 bar size. So we'll do a number 6 bar. And okay, it's been a little bit more expensive because the product up until recently has been, let's just say 10 or 15% more expensive than the steel solution in, say, epoxy. But all of a sudden, what we discovered is we blend in some of the fibers into this mix, and they impart extra flexural tensile strength. And all of a sudden, we've discovered a blend of 15 pounds of fiber in a cubic yard, and we can now take that 6x6 grid and turn it to 8x12. Okay, we're using a lot less bar now, and we're getting the same type of performance. We're getting fatigue performance, cyclical performance. We did all those tests, 1 million cycle fatigue tests. And now when you start to run the numbers cost-wise, we're now at the same cost or less than the epoxy-coated or galvanized bar solution. So this is the real aha moment that's coming in FRP composites. And we couple that now with the fact that the ACI is going to institute later this year or publish a full-on FRP bar code. Usually one of the questions from the engineers was, well, are you in the code? And we used to say, well, if you're talking the 318 design code, we're not mentioned there, but there's a separate committee that has a design guide. Well, they've now taken that guide and codified it. So this is where we're headed.
So fiber reinforcement, rebar, and fibers, you're saying is going to become more mainstream, because right now it's not. Mainstream is typical, steel rebar,
Right.
and that's what's in all the code books that all the structural engineers reference. So I had like I shared with you, Al, I've had folks reach out to me and tell me about fiber reinforcement. It sounds like it's getting more attention now because of the cost of steel has gone up. So it's now got to a point now where those costs are parallel with the fiber reinforcement. So now fiber reinforcement is getting some consideration, but it's not mainstream. It's not a known factor as far as like you said, code or what the structural engineers know.
Right.
I think one of the things that got me involved in this, because I was doing an extensive amount of work with Dr. Nani at the University of Miami with some of the other products that we get involved with, the Florida DOT, which has been one of the leaders in the country, the following statement is what caught my eye. We're switching over to non-metallic rebar because we want to increase the life of our structures from 50 to 150 years. If economists don't get that, then they shouldn't be economists.
And another aspect of that from Florida DOT, which is where I live now, is that we were in a conversation the other day, and they've got almost a $1 billion budget down here in the DOT to spend every year to either maintain or build new infrastructure. And what they said is he said almost half of our budget, almost $500 million a year, we're spending not to build new stuff, but to fix the old stuff. And that's the problem. And he said, when we say fix the old stuff, some of this stuff is only 15, 20 years old. We're having to go in and doing repairs. One of the little idiosyncrasies of Florida is they tried epoxy-coated rebar years ago and had a very bad experience with it. And they eliminated it. They prohibited it. It's actually in the DOT specifications. You cannot use epoxy-coated rebar in this state. So they've been using plain steel rebar and trying to increase the cover on the bar for protection, and it's not been working. So that's why they are now fairly well committed to using FRP composites. They're looking highly at stainless steel. And stainless steel is great too, but it's very expensive. I mean, that's way out there.
Right.
But the key is, as you mentioned, the engineers were not taught this in school. And the difference for the engineers is that these fiber reinforced polymer composites, they're stronger than steel. But they have what they call a lower modulus of elasticity. What does that mean? They're stretchier. They stretch further. Under load, they stretch a little further. So when you start to load a deck or any beam, if the material starts to move down and whatever, it crack, and then you got to put a little bit more in there to make sure we compensate for that. And of course, that's another thing that we found with the fiber. The fiber helps to strengthen this flexural resistance, so that helps.
So is Florida the DOT down there? Are they using both? They're using the fiber rebar and fiber reinforcement in their new designs, or what does that look like?
They're focused a lot on fiber reinforced FRP rebar is what they've been comfortable in right now, and we're getting them into using more in terms of fiber. Again, we have an issue of having to get it specified. And how do you write the specification for this? Especially since there's all these types of fibers in there, and you've got to start to classify which fibers you want to use. You probably want to use a macro structural fiber as opposed to a micro in there, or you might want to do both. Frankly, we just did there's been studies where they've done blends of fibers, and that they've worked out quite nicely. So there's tons of research going on regarding this, and there's a number of states that are highly interested in the FRP bars. I'll just tell you another thing that's going on that most people are not aware of. AASHTO is the American Association of State Highway and Transportation Officials, and they write the code for bridges. and they also have all the. They basically, when you become an engineer, you typically either go the bridge side or the building side. You're a structural engineer in buildings and structures, or you tend to go towards civil and bridge and that type of thing, and you tend to work in either one of those codes. There are a few people that do both, and then there's those of us who have to work in all these fields, so we tend to become familiar with it. But the AASHTO people are becoming so, in the federal government, FHWA, are becoming so interested in this that they've said we've got to standardize and certify these products. And that's been one of the things that's been going on in the industry is you've got a number of different suppliers of these bars. And what happens is they each make a slightly different product, as opposed to steel rebar, where that's been highly standardized. ASTM standards for the bar, and yes, you will have some different mills that are rolling different deformation patterns on the bars, but in the FRP world, for instance, you'll have people who have deformations, you'll have people who have sand coatings on the bars, different types of things. They all work, but they're different. And so now we're getting to the point where they're standardizing them down. We've got the ASTM tests that are now, a few years ago, those got standardized. That's been very helpful. And AASHTO is starting to develop a standard system for that. They call it the NETPEP, is the acronym, the National Transportation Evaluation Program, and Product Evaluation Program. And so once we have that, a manufacturer will be able to go into AASHTO NETPEP, submit all their testing, and there are, I believe, now 28 or 29 states that are accepting this program. So you will instantly be accepted in all these states. Right now, there's probably somewhere between 6 to 12 states that are highly active in terms of using fiber reinforced polymers. One is Maine, for instance, and others South Carolina, Ohio. You know, they're all over the place in terms of using it.
And can we talk a little bit about the manufacturing of these products? Where are most of these manufacturers at? Are they here stateside, overseas? Where are these folks at?
Variety. There's a variety of places. There's some that are coming from overseas. There are several of the manufacturers in the United States right now. They're making them here. There's several up in Canada. Canada's pretty strong on the FRP bars. And so there's a few up there that are very good. There are people that are bringing product in. And, you know, in terms of what they call Buy America, that program, which is the Buy America program, is for federal highway. And that used to be just for steel. That's all that was concerned with. Actually, when it was originally done, it was both steel and cement. They were concerned that they wanted it all made in the United States. Unfortunately, most of all the cement suppliers now, they're made here, but they are owned by foreign companies. So on the steel side, it's been basically a made in America steel program. That recently got expanded, and now it's becoming a make everything here. And so we're doing that. We're making the bar that I'm representing, this G-bar product, is being made in Ohio. And the fiber that we currently have here is made in Norway, but we're planning to make it here very soon. That's the plan.
Okay, and can you talk a little bit about the process, the manufacturing process? How is the bar and the fiber made?
This is the manufacturing process is referred to as pultrusion. And when you're a kid, you may have had a Play-Doh fun factory like I did, and that is an extrusion type thing where you push material through a die. Pultrusion, what happens is that we have the fibers themselves that come off of spools like thread, and then they go through a bath of the polymer resin, and then they are pulled through a die at the right shape and under tension and squeezed, and everything gets squeezed together. And then as soon as that happens, and whatever texture is applied to it, or if there's a deformation, that's part of the process. And then that whole bar now that's been coming out of that die is now drawn down into an oven. And that, of course, is where we heat it, bake it, and that's what cures the resins. So we use what is called a thermoset resin, which means it needs heat to cure, and then once it's cured, that's it. It's a solid piece, and it can't be bent or anything thereafter. That's by the way, that's another issue that we have to make sure that people understand, is that these bars, as they're made, we need to do any bends, or we need to do stirrups, whatever, that has to be done as we're making it, because we use a thermoset resin. And so those are made in the factory and made to spec, and it's no problem to make it, but it's not something that is done out in the field. There are companies that are now experimenting with what they call thermoplastic resins, and they've made some very good progress with it. And the idea there is going to be that we'll be able to make these bars with a thermoplastic resin eventually, and then they'll be able to be sent to, say, a rebar fab shop. And the rebar fab shop will have a machine that would be sort of a bending machine, but it will also have a heater compartment. And so that will reheat the bar to the exact right temperature that they can do the bend. And that will be done in the shop. We're waiting for that technology to really come out and be commercialized right now. But in the meantime, we can supply all of the bent bars and fancy shapes and whatnot the same thing that you do with steel. It's just that we have to do it when we do it at the factory.
Right. And did you mention what the raw material is? What is it made out of?
The two components are, one is the fiber, and the fiber would either be, usually it's a glass, and there are various types of glasses, but usually it's what they call an ECR glass, a type E glass that's corrosion resistant, and it's paired with a form of polymer resin. Now, the resins that are commonly used are vinyl ester resins, just one type. And the other one that's used is an epoxy resin, and both are quite valid and work beautifully. And it's just which system your particular pultrusion machine is set up to use.
Gotcha. And all this is readily available material.
Oh yes, very much so, and made in, depending on the fiber, made in the United States too. That's the other thing. The glasses are made in the United States. There's now basalt, for instance. Basalt fiber is now being made in the United States. Some of the fibers are more exotic, carbon. The other two fibers that are typically out there that are used are the carbon fibers. People hear about carbon fiber pieces and parts and whatnot, and airplanes and whatnot. Those things, some are made over here. Some carbon fibers are coming from overseas. And then there's an unusual fiber that people may or may not have heard of called aramid. And if you know what a Kevlar vest is for personal protection, that's made with an aramid fiber. So there are people that have used aramids, but again, it's a specialty type fiber for a certain type of application. One of the interesting things about the high end, the carbon fiber, and even the basalt actually, is that it can be pre-stressed. Carbon fiber, there's carbon fiber cables that are used for pre-stressing and do a very nice job. They're very expensive. But then we also have a version of one of these basalt bars that we have that we can do a light pre-stressing with using the standard equipment. That's another new feature here. We've discovered that we could pre-stress these bars. And it's light pre-stressing. It's not the type of normal thing that most pre-stressed concrete companies would get into. But if you just need something for what I'll call handling purposes, just to lightly pre-stress the member to get it out of the casting bed, put it into storage, move it around, and then usually it's a member that you would then turn vertical, like a column or a wall or something, and then after that, it acts like rebar inside the member, not so much as pre-stressing anymore.
I gotcha. Okay, so let's talk a little bit about I imagine that installing fiber rebar in the field is different than normal rebar. How do we tie it? What does that look like? Well,
installing fiber rebar in the field is almost exactly like using steel rebar, except it only weighs a quarter of that of steel. So it's so much easier to handle and so much lighter and so much easier on the guys. in working in the field, guys and gals working in the field, the crew out there is so much, it's nicer for them to deal with it. And so this is something that people are finding is that things tend to go faster. And so, as you know, in the field, you have to tie the bars together. You're not just generally laying bars out. You're usually crisscrossing them and tying things together. And normally in steel, we use tie wire. And there's these tie wire machines and whatnot. And there's a version of the tie wire that has been developed and used for years for the epoxy-coated products and the galvanized products. And it's a plastic-coated wire. And you can use that. That would be a perfectly acceptable tie wire to use with this because it's going to be protected from its own corrosion. Again, the tie wire is not critical. The only thing we could possibly say is that we wouldn't want any of these little tie wires to be sort of sticking up too close to the surface such that they would cause a little corrosion themselves and a little pop out or whatever in the system. But what we've really been doing lately is using zip ties. Everybody, I think a lot of the construction people who understand what a zip tie is, it's used in wiring and plumbing and all these types of things. We use zip ties. There's even a zip tie gun now that will tie the things together very quickly. So that's part of it. And there's a company out there, is a proprietary company that makes a plastic clip. And they can clip these bars together. As long as you've got the same size bar, crisscrossing at a 90 degree, you can use these clips and pop them into place too. Very fast, very quick. As a matter of fact, a lot of cages would be done that way with same size bars, that would be the solution I would pick right away. And then for any bars that would be either at angles or at maybe two different bar sizes, I would then use a zip tie for it.
Yeah, I would think.
Yeah, the other big item you want to concern yourself about is concrete cover. All concrete cover is based upon corrosion. So that's going to be a major issue with regards to reducing the volume of concrete necessary to produce a particular concrete member.
That's correct.
So you're saying it requires less cover? Is that what you're getting at?
Oh, yes. Yeah. We don't need the cover. Actually, the only cover we need is the amount of concrete that's required to develop the strength of the bar. So we usually can go down to, of course, it depends on the size of the bar, but a lot of times you're looking for these outdoor or exposed conditions. You're looking for a couple inches of cover, and we can usually get down to 1 inch of cover is perfectly acceptable. And that can help. And so then what we do is we tend to then reduce cross-section on a wall, whatever it might be, a slab on grade. We don't have to have the amount of concrete. That's where some of this starts to get really interesting because all of a sudden you're switching over materials. And let's say that, if you take out the steel and put in the FRP composites, well, the numbers don't look right. And the FRP composites look more expensive. But then you say, well, wait a minute, I can reduce the amount of concrete I've got. Oh, that makes a big difference. And then the other thing that plays into it nowadays is everybody's concerned about carbon footprint. And, of course, the concrete is the real carbon footprint gorilla in the room. And so if we can reduce the amount of concrete going into a job, we're really making a difference. And, of course, the concrete people are all making their changes. They're doing better cements. They're doing different formulations. We're all working on that. But this is a big game changer. And so we found that we've done several analysis, for instance, and if I can do a changeover from a steel reinforced concrete slab to a fiber reinforced concrete slab, I can, with reducing the amount of concrete a little bit, maybe going from a 6-inch to a 5-inch, 6-inch to a 4-inch slab, maybe something like that. I can take out your carbon footprint. I can reduce your carbon footprint by almost a half. So that.
And there's also another hidden expense which is not eliminated, but reduced dramatically, and that's shipping. When you start talking about shipping costs for all of these items, it's all based upon weight. And when you can take and reduce your cross sections, the shipping costs get dramatically reduced as well. These are all the things that aren't being considered when people just look at the cost of a bar.
Right. So you're saying, I guess, let's talk about the limitations of the fiber rebar. Can we like say in a parking garage? I always go back to parking garages. I've built so many, so you're gonna have to forgive me. But the parking, like a parking garage beam, like instead of having all that big steel rebar in the parking garage beam, can we do fiber reinforcement in those now?
Yes, absolutely. Yeah, we should be looking at these things, and not just to go from steel rebar to fiber FRP composite bars, but use the blend of bar and fiber in the FRC. See, I talk about an FRP FRC. So an FRP bar, fiber reinforced concrete, fiber reinforced polymer, fiber reinforced concrete. And that's the real key here, is the hybrid blend of the two. And to have an engineer that understands that. And there's two different design guides for it too. I mentioned the 440, ACI 440 for design for the bar. There's also ACI 544, which is for fiber reinforced concrete. So we have to blend in the two design methods again. And again, this is why this has been slow to take off, because it's not something that most engineers are taught in school. They get the basics and then they go into practice. So we're always in an educational function here. And what we're doing, frankly, is we're providing a lot of complementary value engineering from the companies here. We have the engineers that know how to do this. And so we provide them with the design help and the design calculations and say, here, this is how it's done. And then all the engineer of record has to do is review it and check it, make sure it does fit what he's looking for. And then that very helpful, and then brings them up to speed as to how to do it.
Right. Yeah, I think to make it easy for them.
Oh, yeah.
They either need to reach out to people like you, or we need to have some kind of conversion calculator for them to pop all that in there and spit it out, so they don't have to think too much.
Well,
that already exists.
That already exists.
Yeah.
Of course. Okay.
Well,
we plan ahead.
Or you've done this before, right?
A little bit.
So we talked about you can't bend it in the field, which I can't tell you. Maybe a handful of times I've seen that happen with rebar. Normally, at least the stuff that I'm used to is so heavy duty, you're not bending that size bar out in the field by hand anyways. So if we're getting to a point now where, that was kind of the pushback that I was giving folks that were reaching out to me the last couple of years with fiber reinforcement. I was like, hey, this is great if I'm going to go build a house and, I'm going to put this fiber reinforcement in for like a slab on grade or something like that. I can see the utilizing it for that. But if we're talking about now, we're getting to a point where we're comfortable using these products for, for heavy structural type, like you said, bridges or, buildings and again, parking garages, then I think, we seriously need to consider this, especially since our friends in the steel industry are passing on their costs, and the price of rebars is even right now. We're recording this near the beginning of August of 22 is double what we've seen in the past. So this is I think a great option that we need to consider. So if we can truly swap out this fiber rebar for steel, another thought that came across and it probably popped in folks' mind is if you're making the overall structure lighter as well. So a big cost for projects is as we get into maybe utilizing real estate that's not ideal. We're having to do a lot of ground improvements, a lot of deep foundations, things of that nature. So if we're making the building lighter, to make those the design of that as well. I guess not requiring as much money as far as improving that sort of thing as well. So there should be some savings there if we're making the overall building lighter. Is that something y'all have seen before?
One of the things you want to think about in addition to that is with the new technologies that are coming in, like 3D printing. 3D printing makes a lot of sense. It's a very efficient method of using concrete, But the follow-up to the 3D printing is now getting a lot of feedback or pushback with regards to potentially shrinkage cracking. So the idea of introducing both the fibers into the mix itself and being able to lay these bars as the various courses are being increased, the whole concept of 3D printing is something that interests a lot of people, but then there comes up some negatives associated with it. Again, we look forward to providing the answers to make it a better product in the field and make it much more feasible. And that's just one aspect of where this could be used very effectively.
Yeah, we hit on that topic on an earlier podcast. We talked a little bit about 3D printing, and the fellow I had on the podcast, we talked about how the 3D printer's got to be more versatile than spitting out the concrete. It needs to be able to spit out the rebar, the reinforcement, as it's printing or whatever you want to call it. Because right, like you said, the shrinkage cracks, and I'm sure there's other things that the 3D printing world is not sharing with us, because it can't be going perfectly. And I get kind of I question things that are subsidized by the government. So if it's being subsidized, that tells me they're covering up something as far as cost or something, issues that they're having. So in the long term, I don't. Or in the short term, maybe that helps out, but in the long term, you're not making things, I guess, cost efficient. So it's not going to be competitive down the road. So when we're
if you're looking at macro structural fibers, you've basically taken the labor out of it, because these are basically just like any other admixture. So they're basically delivered to the project.
Yeah. Yeah, no. I shared with you guys before. I've used my macro fibers before. There's a very big company out there. Every time you build one of their warehouses, they have macro fibers specified in all their floors, slab on grade, and even the slab on metal decks. So it's a good product that obviously they build thousands of these facilities across the country, so they must know what they're doing.
Well, they're using that for crack control, Seth, and I'm aware of those companies too, the big warehouse people, and they're using robots, floors, and they can't afford any sort of crack, so it messes up the forklifts, and especially some of them the robot units that they're using. That's we can supplant that.
Yeah.
And what I'm talking to some of those same companies is that we are looking at a lot of times those warehouses, how heavy duty they are, they'll actually still have rebar in those components as opposed to the fiber. And we're talking about literally supplanting the steel bar with these now new FRP bars. They're much lighter, easy to deal with. They bring up these bars on so many levels, and it's too heavy, and the guys get worn out using it. Place it.
Yeah, no, it definitely. I like I said, I think it's now that we're getting to a point now that that the fiber reinforcement is getting in ACI, and it's being considered for bridges and things of that nature. I think it's definitely something that we need to explore, and folks need to reach out to experts like you and decide if this is a possible solution for their project. But I think that's a good spot for us to end today's show. Pat, if folks want to reach out to you, what's the best way?
Well, the two ways they can reach out to me is either through my office, 203-467-4426, or just visit my website, www.ConSpec, as in concrete specifications, conspec-rep.com. Those are the two easiest ways to reach out to me. And if you can't find me, just go to LinkedIn. I take up about half of it.
And Al, how about you if they want to reach out to you? Go ahead.
Oh, yes, Seth, that's it's not hard to get a hold of me, but probably the easiest way is to use my email address. And I'm also on LinkedIn, as you know. We're connected on LinkedIn, so that's another way to get a hold of me. But my email address is acericson, and spell it right. It's ACERICSON at msn.com, the Microsoft Network. And I use that as it's a personal email address, so it goes direct to me and not through any of the companies that I represent. So that's how you get a hold of me. It's the best.
All right.
And you can tell the quality of this presentation because everybody has a beard, so that it must be correct.
That's right. Gotta have one.
Absolutely.
Yeah. I appreciate y'all coming on the podcast, and we'll all your contact information, as always, we'll put in the show notes for folks so they don't have to listen to the end here several times to write all that stuff down. But we'll make sure they know how to get a hold of you. Again, Pat, Al, appreciate you being on the show today, and we'll have to do it again.
Absolutely. Look forward to it. Thank you for the opportunity.
Thank you for joining us for another Concrete Logic podcast episode. If you got some value out of this or you enjoyed it, please share it with others. And if you could take a moment and give us a 5-star review on your favorite podcast listening app, I would appreciate it. We will catch you on the next episode. And now Mike Dunton's going to take us out.
That alarm always sings couple hours before the sun comes up. Open up the side, put some diesel in the lights and wait till the trucks roll up. Yeah, this ain't how most folks live their lives, dripping in sweat, working overtime. But while they're tying their ties for their 9 to 5s, we're out here changing these skylines with wood, iron, and mud. We work hard for $1, give thanks to the Lord above.